Hi, everyone. Thank you so much for tuning into the fourth edition of the AESIS newsletter interviews. And we're very glad today to have Daniel Huppmann from YASA with us. And to get started, maybe I can ask Daniel for you to introduce yourself. So who are you and what is your position in the science ecosystem?
Thank you so much for having me for this interview. Looking forward to the discussion. First, let me start by introducing IIASA. We are an international research institute about 15 kilometers south of Vienna, Austria, and we have about 300 to 400 researchers. It's difficult to put a direct number on it because there are a lot of semi-affiliated people, so researchers who are affiliated with us, but then also at other universities. We exist for exactly 50 years, so we have a big 50-year celebration coming up. And the mission of YASA is to bridge. It was established during the Cold War, East and West, so that's also why it was located in Vienna at the time, as a bridge between East and West, but then also between different disciplines. So systems analysis is what we do, so to tackle the research questions of the day that are too grand and too complex for any particular industry to tackle. And of course, at the moment, the Sustainable Development Goals and the climate crisis are the two topics of the day that we focus on here at YASA. I'm working as a research scholar at the Energy, Climate, Environment program. We are about 60 to 70 researchers in that program, and within that research program, I am coordinating a team of research software engineers. So we develop scientific software and tools and database infrastructure for researchers. So that we can talk about this later, maybe in a bit more detail, but we support researchers in their work. So we give them the IT infrastructure and the tools that they need to do their analysis, to do model comparison studies, like what you see in the IPCC reports. And my role is the interface between the software developers, the research software engineers, and the scientists. So I try to translate between these two groups of people.
Great, thank you. And so in addition to your work researching climate change, you also work a lot with software and with the open science initiatives.
Right, so this is becoming more and more prominent, that there's a call for open science where everybody agrees to in principle, but then how to actually do this and how to move in a direction of open science, it's complicated for a number of reasons. What I think is great is that it is becoming more prominent. So you see more and more journals asking not just for the data, but then also for the analysis scripts that are being used to generate figures, so that these analysis scripts are also published together with a manuscript, so that it is possible for other researchers to not just read the text, but also see how did they actually create that figure. There are so many different approaches for how you can do a certain analysis. Like even if you do statistical analysis, how you compute the mean and the outliers, there are these fine nuances. And it's basically impossible to describe that even in the supplementary information of a manuscript. So if you publish the code, then everybody can go look at the code and say, okay, this is the method that they actually used.
And I'd love to hear more about your thoughts on this, because in a blog post you wrote for the YASA blog titled "Open Science Has to Go Beyond Open Source," you mentioned that to live up to the expectation of truly open science, the research community needs to move beyond only open source. So I wanted to ask what you mean by truly open science.
Let me first try to explain what open source means, because it is a term that is floating around and people have a vague idea of what it means, but there are a couple of misconceptions. So let me try to explain that first, and then you can say whether I explained it sufficiently well that you understood where I was going at. And if it's not sufficiently clear, I can try again or give up.
Sounds great.
If you take a newspaper article or some report published by an NGO or a lobby group, then it's obvious that you can read that article and you can be inspired by it, you can rewrite it with your own words, you can quote directly from it, but it's not okay to take a large chunk of that newspaper article and publish it under your own name. Or you cannot usually cite like 10 pages out of another report. That would be plagiarism. So we have a very good understanding of how this works with text, but the same right, so the same copyright in principle applies to scientific software. So if I write an analysis script, and even if I put it on my website, then in principle, the same rules apply, that other people can look at it, they can be inspired by it, they can maybe like take 2 or 3 lines, but they cannot just take it and run it on their own. In the same way that you can't do that with a journal article. Now, what open source is usually understood as, or too often understood, is that open source means people can look at the code. So I put it on the website and people can look at it, and then that's open source. But that is not how it's understood within the community. There, open source has a much broader interpretation. And that is that you cannot only just look at the code, but you're allowed to reuse it. You're allowed to modify it, and you're allowed to share the modified version again. So it's not just the source code is open in the sense that other people can look at it, but they have every right to use that code for any purpose. So that is the main drive of open source. So if I just put my code on a website and people can only look at it, but then what I have to do is I apply an open source license, and there are several standard licenses that one can apply, and then you can go down that rabbit hole of why there are differences between these licenses. But the important part is that open source means not just looking at it, but being allowed to reuse, modify, and redistribute. And a lot of researchers have now understood that, and what they do is they write their analysis scripts for a scientific journal publication, for example, and then they put it on GitHub or GitLab or a similar service, put an open source license to it, and then it is open source. So that is a good step compared to how research was done 10, 15 years ago, because now other people have the right to actually reuse that scientific software piece of work, where scientific software, it can be a model, it can be an analysis script, it can be something for data visualization, it can be database infrastructure. But open source is not enough, because open source does not mean that people can actually reuse it with reasonable effort. Open source just means that they have the right to do that. But if I give you a piece of software and then you need half a year studying it to understand how it works and how it can be adapted to suit your use cases, then it's basically no use. And this is what I meant with, we have to go beyond open source. We have to put a number of better scientific software development practices into our everyday work, including better documentation, including automated testing, so that you can be sure that that the code actually still does what you think it should do. And that is another rabbit hole that one could go into.
That was a clear explanation. So open source is a piece of code that is, for example, on GitHub, that anybody, if they think this, for example, this piece of code that runs a certain type of analysis is also applicable to their data, they can take it and use it in their research. As long as they credit you, it's free for anybody to use.
Right. The credit part is a very common restriction on open source. You are allowed to use it if you do credit.
I see. And so you mentioned you wanted to explain open source a little bit before you move on to explaining what you meant in the article by a truly open science. So I'm guessing you're going to move forward into explaining a bit about the FAIR principles.
Right. That is one very important aspect of how we can move beyond open source. And FAIR stands for findable, accessible, interoperable, and reusable. And these are 4 high-level principles with a number of more specific specifications on how or what that actually means, what was intended by the people who put together the FAIR principles, but it is a step in this direction of being truly open science. So one very typical example is, how do you make your work findable? Because if you put it on your website, say you have a project that runs for 3 years, you put your scientific software, your data on that project website, but then the project is over and the funding for actually paying the website or the server and the domain runs out after a couple of years, and then the website is gone and people can't access that data and that work that you did anymore. And one way to do that is to move to a common repository, and Zenodo is one, probably the best service available for general research work in that domain. And what they do is they give you a digital object identifier, so basically an address similar to an internet URL. And this DOI, digital object identifier, will exist basically forever. And you can be sure that even if your project website dies after a couple of years, people can still find your work on Zenodo or on a similar repository. And then the other principles: accessible, interoperable, use standards that are used within your community, add a license to your work. And here, one misconception is that the FAIR principles demand that work is open source. This is actually not quite true. So what the FAIR principles state is that it has to be clear how and if other people may use your work. So it does not have to be open source in the sense, oh, you can use it, but what the FAIR principles demand, that the license, so the rules and regulations, whether other people are allowed to use it, that these are clearly specified. So that if I come to another data set, like I'm looking to do some research on some topic, I Google, I find, oh, there's this cool data set. And then the idea is that I can very quickly see, am I allowed to use that data set for my work? And not have to browse then in a PDF attachment somewhere on page 227, there is a small note. No, this should be obvious. And then the generalization of this, it should be obvious, is what's called metadata. So what the FAIR principles are very, one of their big recommendations is that you should add metadata so that somebody who sees a piece of software, a piece of data, immediately knows what it's about. Obvious metadata types are author, year, a title, the license, but then metadata could also include which programming language did you use, or where did you get the source data from that was used to create that data set, etc. So ideally, just from looking at the metadata, a person can grasp what is inside and how was it created and what can I use it for.
So although open source movements and Planet's initiatives are making it more and more common that data is made publicly online, what are some problems that still persist with documentation of code and compilation of data?
Yeah, that's a great question, and one that will be with us probably for at least another decade, because we are in this big transition phase towards requesting open science, open data, open source scientific software. But one of the obstacles is that it's not taught in a way at university that people can learn how to use a version control system like GitHub. You can go to a master's in engineering at many universities without having had to use GitHub ever, without having to write a unit test, like to adopt some of these scientific software practices that help you write better code. So teaching will need to adapt, I guess. Also, what's the difference between the different open source licenses? Why should you use it? These topics are not yet standard part in a university curriculum, even though a lot of engineering and natural sciences is more and more scientific software dependent.
If it's not common in the curriculum, how did you start using GitHub and understanding all about the FAIR principles? Did you just go out and find it yourself, or did you have a supervisor teaching it to you?
No, I had an office mate. So at the time when I joined IIASA, another postdoc started. We shared an office. His name is Matthew Giddon, and he had actually learned it during his PhD. So he had adopted all these best practices, etc., how to do that. And then I looked over his shoulder and said, this looks like it could help me. And then I had somebody to ask. So basically, whenever I ran into a roadblock, I just looked up and said, hey, Matt, like, what did I do wrong? And he would look more or less amused and come over and say, okay, this is what you have to do, and this is where you went wrong. And I think that this is the best way to learn, like have someone show it to you. And it's interesting that you mentioned the word supervisor, because this, I think, is the next, apart from the teaching, the next obstacle to adopting these practices. A lot of supervisors are not familiar with that either. So if you are a university professor and let's say you supervise a master's thesis, then you obviously read the manuscript and you look at the methods and you question the data and the scientific methods, but you usually don't have the time, but often also not the know-how to look at another person's code. So it could be just that you're familiar with Python and the student that you're supervising wants to use R because that's what the student is more familiar with, but then you can't help in a meaningful way. So supervisors not knowing how to do, but also not having the resources in terms of time to supervise well is another big obstacle here. It's getting better over time, I hope, but that is similar to the teaching, another obstacle.
Yeah, and I suppose it also comes with whether they have the incentive to learn what the students are teaching, right? Maybe you can talk a little bit more about your thoughts on the reward systems at universities.
Yeah, we had a really good workshop a couple of weeks ago hosted by the OECD and CoData on what are the obstacles and the incentives and reward systems come up a lot in that discussion, because the whole scientific career mode is built on citations, basically. So you publish a manuscript, and if other people think it's good, they'll cite it. And we know that there are issues with citations, and that you have to take it with a grain of salt. But at least there is a number that you can compare across researchers. This gets more difficult if you look at data. So if I create a cool data set and 10 other people use it, then I can measure like how often was it downloaded. That is a number, but that is, I just know that they downloaded it. I don't know if it was actually useful. Whereas if other people cite my manuscript in their manuscript, then I know that they found it sufficiently useful to actually reference it in their future work. If somebody downloaded my data set, looked at it and said, no, I can't distinguish that from the download number. And then the more and more you go into scientific software, it becomes even more difficult to find a number that you can look at. So if you're in the Python community, then the go-to package for working with data analysis is pandas. But then when I use that and I write my scripts and I create some nice plots for my manuscript, but I would not cite pandas in the manuscript. That would be kind of weird. Or if I did that and submitted it to like Nature would look at me like, why do you cite that? Like that's not relevant for the actual work. So it becomes more and more difficult the further you go away from text to find a useful metric. But then if you have no metric, how can you build an incentives and reward system for it? And if we fast forward 10 years into the future, I mentioned metadata earlier. Of course, ideally in 10 years, if I write a cool paper, it's published in a great journal, I publish also the source code, and then in the source code metadata, there will be some entries. Yes, I use the pandas package, I use these packages. So 10 years into the future, it will be possible to do these crosslinks. The question is what happens until then, and how do you get people to start using better practices like using metadata, etc., if the rewards for that may materialize 10 years from now.
I see.
And it questions, like, if you're an early career researcher, where do you spend your time on? Developing a open source package that will be useful to hundreds of people, or trying to get a Nature publication. And we all have limited time and resources, and then our expectations of the future reward system will influence the decision what we work on today.
And could you talk a little more about the role that publishers and journal editors play in how code is documented and shared online?
Right. So we are moving in a direction where journal editors understand that this is important, and also professors when they're supervising their master thesis. But at the moment, often that means you just put some code somewhere, and then that satisfies the requirements for a submission to the journal. So at least it is somewhere, there's an open source license, but does the code actually run? Does the code actually produce the figures that are shown in the manuscript? This is very time-intensive work to do this kind of validation. And we already have a review system that is getting more and more strained. So I'm also a topical editor of one open source journal in the domain of climate change research. And it is super complicated to find reviewers willing to just read the manuscript. And if you tell them, oh, please also look at the code and please also do that, then it will be even more difficult to find people who are capable and also willing to do that kind of work. So we are requiring that manuscripts are open source, like what Plan S does, good step. Requiring that the data and the scientific software is available somewhere under its open source license, good step. Does it actually have documentation, and does it have the right metadata? It's just a lot of effort to do this validation, and it's not part of the standard workflow for any journal at the moment, as far as I know.
So for most journals, when they get a submission for code, for data, it's not being run through, they don't check it or make sure that it follows a certain standard. It's just as long as it's there, as long as it's accessible for other researchers, we'll just leave it there and people can take it up however they want.
Yeah. But then is it actually possible with reasonable effort to do that? It is complicated. And I have to admit, like, I also fall into this trap. So when I hear some colleagues at other institutions are writing an open source package and I say, oh, this looks cool. And then I look at it for 2 minutes and then, it's on my to read next weekend list. But somehow I never get through that list. And then even though there might be this cool package that could save me a lot of time, I don't have it on my radar, and then I reinvent the wheel instead of using that other package that would save me a lot of time if only I had worked through my weekend reading list.
So I understand that at IIASA there has been effort put in to try to standardize how data is being compiled, how it's being used, and I understand that it's the responsibility of a data steward.
Right. This is an initiative that started almost 2 years ago as part of growing out of a workshop that we did together with CoData. What we have now established over the summer is that in each research program, there is one dedicated person as a data steward. And their role is that they support researchers in managing their data. For example, adding metadata tags, And so when a researcher says, hey, I want to, I'm publishing this paper, it was just accepted. Now, what do I do with my data? And then ideally the data steward says, okay, you go to Zenodo, here is how you upload it. Here are these different licenses that you could use for your use case. I would recommend that license. These are the metadata that you should attach when you upload it to Zenodo. And I think that this is a really good initiative, formalizing a role that is already happening in a lot of research programs. There is usually the one person that you go to for these kind of questions, but now by giving this person like the hat so that they can wear that officially, it's a nice recognition. That this is an important work, that this is not just something that should come at the end after you have published a paper, but this is something that you should think of already as part of your research project. And in my team, or in our program, we have the scenario services and scientific software team, where we have even gone one step beyond. So we have a data steward, but we also have 2 dedicated research software engineers that work together with the researchers to help them write better code, to write documentation, put it on GitHub, use version control, etc. And not just as an end of pipe workflow. So not the researcher works on this for 3 years and then here is the final code, and then a software developer takes that and cleans it up, but as a collaborative process that goes on over a couple of months or even longer. And that the research software engineer asks the questions like, what are you actually trying to do? Is your code really trying or really doing what you want it to do? Are there better methods to do that? And ideally, having our research software engineering team understand the science that we do, and our researchers adopting better practices, not because they have somebody standing next to them saying, this is where you have to click, this is where you have to click, but learning it proactively and adopting it in their everyday kind of work.
I think we've covered quite a bit of ground with talking about open science. And since you're also a climate change researcher, I thought we could move a little bit into that and talk a bit about your research as well. So my first question about that is, why is the Open Science Initiative important in mitigating climate change?
Yeah, that's a really good question. I think out of principle. There isn't like no specific reason. It's just that research should be done in an open science kind of way. It should be reproducible if other people want to do this. So I was a chapter scientist of the IPCC ESA 1.5, the 1.5 degree report that came out 3 years ago. And as part of my work, so we compiled a quantitative scenario ensemble. Maybe many people listening to this interview have heard about the minus 50% by 2030 high-level statement that came out of this quantitative scenario ensemble that we compiled here at IIASA, supporting the ESA 1.5 process. And as part of when the report, the IPCC report was published, we also launched an interactive scenario explorer where you can look at the data. You can say, what are the models, the scenarios that feed in, what are the numbers, and also the open source notebooks that I developed to create a lot of the figures in the report. They are also available via GitHub. So you can go and look at how did we create figure 2.4 in the IPCC ESA 1.5. I think that nobody actually, or very few people actually look at that script. Like it's, I don't think it will help mankind that the script is open source and people can look at it. But I think we should have the ambition to do our work in a kind of way that if they want to know, they can with minimal effort or with reasonable effort. I mean, you still need to understand how Python works to to understand what's happening in the script, and you need to know how these models work. So there is some effort involved, but at least it is there and people can go look at it. This is not going to convince people who say, I don't believe in climate change. Like saying, hey, I made my script open source will not convince these people. But there are a lot of people who are like not denying that we're facing a climate crisis. And I hope that these can be, can I say, insulated against denialists' arguments by shouting from the rooftop, hey, we did the ESA 1.5 and we really tried to make it as easily accessible as possible. And I hope that this, there are people who are aware of that it's happening, who have read the IPCC reports. There are people who deny it for a number of reasons. I mean, you also see that with the COVID crisis, that there are people who just deny scientific insights for a variety of reasons, and that's definitely not what I can comment on. What I hope is that there are people in between who can be swayed by my ambition and my efforts to make the work that we do here at IIASA slightly more open.
I think with people who don't believe in climate change, or people who don't believe in COVID, vaccines, et cetera, a lot of the times people are prone to confirmation bias, right? If they believe in one thing, maybe they won't look for information somewhere else. But you also mentioned there are the people who are in the middle, and perhaps those are the people that can be swayed, but maybe through the people in the middle and other people you can get through.
Right, and I mean, this is what you hear quite often, like, what is the best thing that you can do about climate change is you talk about it, so that that people are aware that this is a big issue, that politicians hear that their constituents think it's a big issue, and every person has a different perspective, so is maybe the right person to reach that other person. So where I as a scientist will come up as too like ivory towerish, and oh, that's the person who just works with databases and Python scripts. So I'm definitely not the right person to convince a lot of people. But then if you look at the Fridays for Future generation, people who, well, Greta Thunberg and her generation, they said, listen to the scientists. And they are actually listening, like having great conversations with this generation, and then they are the right people to convince their parents and their grandparents. And that is also a role that I take on a bit, like trying to be an advocate for the science that we do, but not just in a very narrow sense, but also in a broader societal engagement kind of way. Mm-hmm. That makes sense.
And why do you think climate change is such a topic that is so full of controversy and polarization? I mean, even to the point where the president of the US has mentioned on multiple occasions that climate change is a hoax.
Well, as I said, now I'm getting way off my scientific turf and just talk as a layperson. But I think a lot of issues come together. One is misinformation. We know that there have been very well-concerted, well-funded initiatives to first deny and now downplay the effects. We don't know for sure if the effects that we already observe, like the wildfires in California, the floods in Germany, we can't really know for sure that these are caused by the heating of the temperature, or heating of the earth, of temperature increases. And yes, statistically, we can show that. That's what the IPCC Sixth Assessment Report, Working Group 1, that came out in August, that showed very clearly there is a statistical connection. But there is this very long, let me call it tradition or history of people denying the facts or trying to downplay the facts. That is one aspect. And the other aspect is that I think very few people, and probably myself included, have understood how big the changes will be that will be necessary to mitigate it. So if we think about how we have to restructure our transport system away from gasoline based cars, eating less meat. A lot of people feel very attached to their diet for sociocultural reasons. So there is a lot of threat or perceived threat. And this is, I think, a really interesting discussion. Like, how much do we have to show the threat of what is going to happen versus the advantages and the co-benefits that we can have? And the one obvious example is air pollution. So if we get cars, or if we, it's not, sorry, I don't want to say get rid of cars, like that is ridiculous, but you can easily reduce, as Paris has now shown, the number of cars driving in a large city by 50% without having any negative effect on your actual well-being. Like if people go more by bike, take public transport, it's not actually a loss of quality of life objectively, but subjectively, like how you think about it, how you perceive it, it can be perceived as a threat. But if we were to get rid of, sorry, again, shouldn't say get rid of cars, if we reduce the number of cars, there is benefits in air pollution, there is less noise. We know that noise causes a lot of stress. We can let our kids run on the streets without being worried that they are run over. So there are a lot of co-benefits that come with mitigating the harmful behavior that we have, that is harmful to the climate, that is harmful to our to the resources that we need for living, but that are just also harmful for our health. And there is this trade-off. On the one hand, you need to show the effects of what if we don't act, but then also the positive aspects of, well, how much cooler, how much nicer could it be if we do act? But it's difficult to convince people of that, or some people.
And to move on to my last question, this is one that we ask everyone that we interview. So in your opinion, what is the most important obstacle we have to tackle to improve the societal impact of science?
I'm not saying that this is the most important thing, so I'm not answering your question, but it's something that I see also from looking back 5 years ago, how I saw myself as a researcher back then and how I see myself now. Then it's a completely different paradigm. So where we as researchers, as scientists say, okay, it's not good enough to sit in our ivory tower and do transparent, open source, reproducible research and hope that people will come and look for it. We have to go out of the ivory tower and be visible, try to communicate better, learn how to communicate better. It's something that we're not taught in a PhD program, or not usually. So that is something that we as a scientific community are in a learning phase. And I think that this is something that can contribute to a better understanding of science in the wider society. One shout out I want to do, and that is to the IIASA Young Scientist Summer Program. So if you are a PhD student, then, or if you know a PhD student to whom that might be interesting, then please forward the message. Every summer, we have about 50 to 60 early career researchers, PhD students from around the world coming to IIASA and work with us. If you're interested in that, if you think that would be a great opportunity, then look at the IIASA website, search for YSSP, Young Scientist Summer Program, and apply.
So I'll link it in the down bar, so anybody watching, just go there, click on it, you'll be able to find it. Thank you so much, Daniel. And it was lovely to have you here today. And yeah, it's just been a pleasure talking to you. So thank you so much.
Well, likewise. Thank you very much for the opportunity to discuss and for your questions. Thank you very much.